Hello and welcome to the Analog Devices Precision Digital Isolation Technology training videos on the fundamentals of isolated gate drivers. This video is the fourth in the series and will focus on how to determine gate drive strength from the datasheet. A common question asked when considering what gate driver to use for an application is, what is the peak current that the driver can deliver? A peak current is one of the most important parameters in gate driver datasheets, but doesn't tell the whole story. Peak current definitions vary between manufacturers, so be sure to double-check each datasheet's definition. This image shows the typical IV characteristics of the MOSFET. Different curves show the variation of the IV characteristics across different processes and temperature. The number featured in a datasheet's title also varies and could be the min, typical, or max saturation current that a part can deliver. It does not necessarily imply that the part delivers the rated current as a minimum current in the linear mode of operation. RDS on of the MOSFET is almost constant while in the linear region. Most applications should keep gate driver MOSFETs in the linear region. The example peak current of one of ADI's parts is shown in the figure to the right. This part is rated as a 2-amp driver. Since the way ADI rates gate drivers is with the minimum linear region current. For this measurement, an external series resistor of 2 ohms is used. This is in line with how the part will be used in the application. We obtain a different peak current in an application with a different series resistor. This image shows the output MOSFET, which is the usual configuration of the gate driver output stage. For a typical application, series gate resistors are used to control the slew rates and for thermal management of the driver IC. In the figure shown, the peak current is measured across the series resistor, or EXT. The measured charging current waveform shows the instantaneous peak along with the other regions of interest. Higher I peak does mean faster switching, but peak is present for a very short time. The flat portion of the graph shows the Miller plateau, which is the time when high current is most needed, but the peak current number in datasheets doesn't account for it during this time. The gate charge characteristics emphasize this, and we can see that the gate voltage doesn't change, and the gate-to-drain capacitor, CGD, is charged during the Miller plateau. The Miller plateau interval is when most of the switching loss occurs, and the driver should be able to transition the MOSFET gate quickly out the Miller plateau region. We can model the power device as a capacitor and a gate driver with a MOSFET output stage as a resistor. Combining the on resistance of the output MOSFET of the driver and the external gate resistor with the gate capacitor, we effectively obtain just an RC circuit while ignoring the parasitic inductances. The RC circuit for turn-on and turn-off is different depending on the value of the resistance. The peak current delivered can be obtained as IPK equals VDD/RG. If the NMOS and PMOS on resistance is different, then the source and sink currents are different. In most drivers, this is the case, and in application, the external gate resistors for turn on and off are also not equal. The current required for an application can be calculated from IPK is equal to QG, total, over rise time. As long as the driver can deliver the peak current to meet this requirement, the driver can be considered for an application. As observed, the peak current is heavily dependent on the on-resistance of the NMOS and PMOS MOSFETs in the driver output stage. RDS-on is therefore the true basis for peak current. Lower RDS-on has benefits almost across the board for gate drivers. The main trade-off is that lower RDS-on costs die area. Since output FETs in a gate driver can be 10 to 30% of the total die area. Thus, ultimately, there is a balancing act between drive strength and price. The energy for charging or discharging any capacitor is CV2/2. The way this energy is dissipated determines the thermal management of the driver. Power is shared between the internal RDS-on and the external series gate resistor. Switching power dissipation within IC is equal to RDS-on divided by RDS-on plus or EXT multiplied by the switching frequency times the total gate charge and applied gate voltage, with IC being the integrated circuit. Lower RDS-on allows for lower IC power dissipation for the same max peak current target in a design. Less IC power dissipation percentage means lower self-heating in the IC. This means higher allowable ambient temperature for the same system. Let's calculate the power dissipation with different drivers in an application when the total gate resistor value is the same. Disregarding the tolerances of external resistors and considering the max RDS-on of the gate driver output stage MOSFETs, we can calculate approximate power dissipation. Using the equation for the power dissipation, we can find the proportion of power dissipation within the gate driver. For the turn-on case with competitor 1, we get P_dis is equal to 4 over 4 plus 1 equals 80%. Similar calculations can be made for the power dissipation during turn-on of other parts. For the turn-off case with competitor 1, we get P_dis equals 2 over 2 plus 3 equals 40%. Calculations for other parts follow. As stated before, the power dissipation within the IC needs to be as low as possible. This figure shows the gate voltage waveform with different parts when driving the same load under the same conditions. We measure the thermal dissipation during turn-on and turn-off transitions when a capacitive load is driven. The two parts are rated for the same peak current in the datasheet title. The setup is created equal such that the external series gate resistor in their path makes rise or fall times of the gate voltage almost equal. The ADI part has an external gate resistor, or GEXT, equal to 1.6 ohms, while the competitor part has an external gate resistor of or GEXT is equal to 1 ohm. In such a situation, similar power dissipation is expected, but the distribution of power between the IC and the external gate resistor means that the temperature rise of the ADI part is lower. The heat maps obtained using a thermal imager show the dissipation within the part, and or GEXT indicates the temperature difference is significant between the two parts. This allows higher ambient operating temperature for the ADI part. The obvious advantage is that it helps to keep the gate driver cooler by spreading the heat in the external gate resistors, and thus better thermal management of the part is obtained. Analog Devices has many digital isolators that provide trusted safety and data integrity. To learn more, please watch the next in our Precision Digital Isolation video training series on the fundamentals of isolated gate drivers. Click on the link below or visit analog.com/iCoupler.